All right, here we go. So system is at equilibrium. First of all, it has nothing to do with grams. It does have to do with rate, so that looks promising. All product, no, that's not equilibrium, and it does not have to do with how many moles of each one. So the only one regarding rate was B. K is products on top and reactants on the bottom. So I know I'm looking for BRF3 on the product side. I also know those coefficients are, or those exponents are the coefficients. All right, for number 3, I'm looking for a buffer with a specific pH range. So I'm going to look at the pKa's of these different buffers. I was given Ka's, so I'll just do minus the log of the Ka's for each one and see what I get for all of them. Now, D here doesn't have a Ka. That's because HCl is a strong acid. So, of course, a strong acid doesn't make a buffer. So that's out. All right, so I have them all here, and it looks like the only one in the right range is, they're kind of misaligned, so C. It's actually, D is the one that was the strong. Okay, so C. There we go. All right. Diprotic acid means there are 2 hydrogens, so I'm looking for an acid with 2 hydrogens. I'm looking for the pH when I'm given the OH minus. So you could do this a few different ways, but I chose to convert this to POH first. And then just subtract from 14 to get the pH. The strongest acid from the list below, in this case, I know HF is a weak acid, so they must increase as I go down. So I'm just looking for whichever is lowest on the periodic table of the halogens, which is iodine. All right, which cannot function as a buffer. I'm seeing lots of things that look like they can function as buffers because they have weak acids and they're salts. But then when I get to E, that is a strong acid, so it cannot function as a buffer. All right, which would decrease the solubility for lead iodide. A couple of these I might have to think about what would happen, but I see right away that this lead nitrate has a common ion, and so I know that would decrease the solubility, so I don't even have to think about the other choices. All right, for this one, I'm looking at a K that is very small, 10th to the negative, what does it say, negative 10th. And so I know if products are on top and reactants are on the bottom, I must have a lot of reactants in order to get that small of a number. And so that would also mean that the equilibrium is on the left. And number 10, whoops, we just did this one. Didn't proofread my work very well. All right, for the acids here, in identifying the acids, I'm looking for something that's losing hydrogen during the reaction. I see the chlorine had a hydrogen, and now on the right it does not. For the second one, I see that the water lost a hydrogen. It can act as an acid or a base. In this case, it did. Because this is an equilibrium reaction, it's also going in reverse, so I should identify one of the products as an acid as well. And then in C, the SO4 lost its 2 hydrogens. All right, for number 12, you could, again, do this lots of different ways, but I'm just going to choose to fill in all my pH and POH columns first by subtracting from 14. And for the ones that I don't have a pH or a POH, I'll do minus the log to get one of them and then subtract from 14. And get all of those, and then whichever H plus and OH minus I'm still missing, let me finish this first. Now I'll just do 10 to the minus of whatever ones I don't have yet. Now, the pHs and pOHs don't have units, but the concentration of hydrogen and hydroxide have units of molarity. All right, once I have all those, I'm going to look at my pH column, and anything that's under 7, I'll say acidic, and anything that's over 7, I'll say basic. All right, next up we have a Le Chatelier's problem, and it's worded a little bit differently. It says which ones will make more products, which in my mind I'm saying shift right. So will it shift right? So for the first one, it's a volume, and so I'm going to look at the number of moles of gas, 2 on the left and 3 on the right. So cutting the volume will shift it toward the less moles, so that would be a shift left. For the next one, I'm increasing a reactant. That would shift it to the right, so I'll select that one. The next one is exothermic, so I'm going to add heat to the product side. So if I cool the reaction, I reduce the heat, then it would shift to the right. And then for the last one, adding neon is a way of saying that I'm going to increase the pressure. So I'm looking at the moles of gas again. I see 2 moles on the left and 2 moles on the right. So doing this neon would not change anything either way. All right, writing our Ks, remember products go on top, reactants go on the bottom, and stoichiometric coefficients become powers. So I'll have CH4, H2S squared on top, CS2, and H2 to the 4th on the bottom. For the second one, remember we're only including gases and aqueous, so I'm canceling out my solids, and I would just have CO2 times H2O. All right, next up I have an equilibrium problem. I have some information about CO2, a little bit of information about CO. So I'm going to write an ice table. Some of it's initial, some of it's equilibrium. And so I'll put everything where it goes. I actually don't care about carbon because that's a solid. So then I'll do my minus x and plus x. The CO is plus 2x. And so that must be equal to 2.4. So I know that x is 1.2. So I can plug that in. And so then the question asked me for 2 things. One, it asked me for the concentration of CO2, or the partial pressure of CO2 at equilibrium. So that would be the 3.8 atmospheres. And then it also asked me for my Kp, which would be CO squared on top and CO2 on the bottom. Remember the CO is the 2.4, and then the CO2 is the 3.8. I get 1.5. All right, next they're giving me a K for one reaction, and then they're asking me to figure out the K for a related reaction. So I'm going to write the equation for each K as the reaction is written. So this would be IBR squared on top, and then I2 and BR2 on the bottom. For the second one, it would be IBR on top, and I to the 1/2 power, I2 to the 1/2 power, and BR2 to the 1/2 power on the bottom. And so when I compare, I see that the bottom one is just the square root of the top one. I put check mark, but I mean square root. There we go, square root. So I can just take that K, the 120, and take the square root of it to get the K for this one. And 2 sig figs would be like 11. All right, number 17, don't be thrown off if it's almost too easy. It's 0.65 molar HNO3, and it's just asking for H3O plus. Now I'm thinking of HNO3 as separating into hydrogen and nitrate ions. Of course, those hydrogen will attach to a water, and that's where the H3O plus comes from, but it will essentially be the same as just H plus, 0.65 molar. All right, next up I have I'm calculating the pH of a weak base. I know it's a base because they gave me a Kb. So I'm writing in my equation, I don't want to write this whole aminoethanol molecule, so I'm just writing B for base and making my ice table. I converted the 1.67 times 10 to the minus 2 to 0.0167 just to make it less cluttered. 0, 0, minus x and plus x. Filled all that in. Okay, then I'm going to write my equation for Kb, which is Hb plus and OH minus, the ions on top, and the whole original base on the bottom. Of course, water is a liquid, so it's left out. And plug everything in. To solve this without the quadratic formula, I'll need to assume x is small, and that just gets rid of the x where it's added on. And solve for x. I'll cross multiply to get x squared. And then the square root. All right, so that gives me my x. So a couple of things. One is I should check if x actually is small. Remember that the way I'm going to do that is I'm going to put x on top, what I got for x on top, and then what I ignored it compared to, so the 0.0167 on the bottom. And then multiply that by 100, and I'm looking for that to be less than 5. And it's 4.3. It's not way less than 5, but it's less than 5. We'll call it good. All right, so then I want to figure out the pH. Right now, x is my OH, so I could get the pOH by doing minus the log of my x. And I get 3.14. That would be the pOH, so to get the pH, I would subtract from 14. And I get 10.86. Okay, number 19 is really similar, but this time it's for an acid. So the acid will lose a hydrogen and leave behind the anion. But my strategy is really similar. I'm going to make an ice table, put in my initial concentration, minus and plus x. Write an equation for K. This time it's a Ka. Ions on top. Whole acid on the bottom. Plug in everything for my ice table. Assume x is small. Cross multiply. And take the square root. And then again, I want to check that x is small. Okay, it's even less small than the last one, but it's still less than 5. We're still going to call it good. And then I can just do minus the log. And this time I'm doing minus the log of h plus is x, and so it'll just be minus the log of x is my answer. No subtracting from 14 this time. 2.42. right, next up I have a molar solubility problem. Let's write the formula for our salt here. We've got tin and iodine, so SNI2. And so that will separate into tin and 2 iodines. I'm making my ice table, minus x plus 2x, x and 2x. Write my equation for KSP. And at this point, honestly, I hadn't even read the question. I just assumed that they gave me the KSP, but now I'm noticing that actually, no, what they gave me was the molar solubility. Okay, so it doesn't change anything. I'm still doing that fine. That would be my x, right? Molar solubility is how much will dissolve, which is x. So that number is getting plugged in here for x and 2x. And now I can plug that into my KSP equation. So the 1.28 gets doubled to 2.56 and squared. Both of those things have to happen. And I can get my KSP of 8.39 times 10 to the minus 6th. All right, next up we have a buffer, and we did a problem like this in class where we were looking for that base to acid ratio. And so I'm looking to see which one has the extra hydrogen. So the H2 one is the acid and the other is the base because it has one less hydrogen. I'm writing the Henderson-Hasselbalch equation. Sorry about the focusing. I'll fix it in a second here, hopefully. All right, so now I'm just solving. So I get negative 0.44 when I subtracted the 7.19 to the other side equals log of base over acid. And then I'll do 10 to the to cancel out the log. There we go. Hopefully that'll stop the focus issue. So the base over acid ratio is 10 to the negative 0.44, which is the 0.36. All right, now we have a KSP problem like I was trying to do earlier. Calcium fluoride will separate into calcium and 2 fluorines. Starting with 0, minus x, and plus 2x. Write my equation for KSP. This time I do know the KSP, 3.9 times 10 to the minus 11th, and so then that would be x, and then 2x squared, which remember that's 4x cubed. Divide both sides by 4. And I get x cubed. Then I can take the cube root. I'm going to do that with like a 3 and then the x root button, but you could also do it to the 1/3 power. And I get 2.14 times 10 to the minus 4th molar. That, yeah, so the molar, that comes from, this is the molar solubility. This is how much calcium fluoride would dissolve, so I'll put the molarity unit on it. Then to get my grams per liter solubility, I will just need the molar mass. Calcium and 2 fluorines. And be, I'm just checking, actually I should only have 2 sig figs, so I change it to 0.017 grams per liter, and I'll actually change this to 2.1 times 10 to the minus 4th molarity, because I only had 2 sig figs in my original problem. All right, and last but not least, we have sort of a traditional buffer problem. I've got my whole acid, which has the extra hydrogen, and my base. I will also need the pKa. They gave me a Ka, so I will do minus the log to get the pKa. And to figure out the pH of the buffer, I'll use the Henderson-Hasselbalch equation. pKa plus log of base over acid. And I get 4.88. When I add HCl, the part that will affect the pH is the H+. It will react with the acid to make, with the anion to make whole acid. So I'll plug in all my initials. I will use up all the hydrogen. Remember, change signs when you get to the arrow. So I'm subtracting and then adding that 0.01. And then I'm back to the Henderson-Hasselbalch equation, 4.74 plus log of, now it's 0.265 for the base and 0.210 for the acid. And then finally, I will have sodium hydroxide added to the original buffer, so that will react with the whole acid to make water and anion. I'm going back to the original 0.2 and 0.275 for the concentrations. Again, I don't care about the concentration of water. I'm using my calculator for these just because with the decimal places, I don't want to mix it up and put it in the wrong place. So 0.16 now and 0.315. Back to Henderson-Hasselbalch, 4.74 plus log of now 0.315 over 0.16. And it should be a little higher than the original, which was 4.88, but not really different. And I got 5.03. All right, that's it. Good luck on your studying and the exam.